So, we will come to another example, that is your example 7. So, it is given that an overhead line is connected in series with a cable. The overhead line has an inductance of 2 millihenry per kilometer and capacitance of 0.01 microfarad per kilometer. The cable has an inductance of 0.25 millihenry per kilometer and capacitance of 0.102 microfarad per kilometer. Now, if a surge having a maximum value of 100 kV travels along the overhead line towards its junction with the cable, calculate A, the surge impedance of the line and cable, just hold on, then then your B, the velocities of wave propagation in the line and cable, and C, the reflected and transmitted waves of voltage and current at the junction, right. If the 100 kV surge originate in the cable, calculate the reflected and transmitted waves of voltage and current at the junction. So, solution, how we will do this? First, you have to compute the surge impedance of overhead line. You know, first say overhead line, say it is Z1. So, Z1 is equal to root over L1 upon C1. L1 is given 2 millihenry. So, it is 2 into 10 to the power minus 3, and C1 is given 0.01 microfarad. So, it is 0.01 into 10 to the power minus 6 to the power root over. So, to the power half, if you calculate, it will be 447 ohm, right. Similarly, surge impedance of the cable Z2 is equal to root over L2 upon C2, and L2 is 0.25 into 10 to the power minus 3, because it is 0.25 millihenry, and C2 is 0.102 microfarad. So, 0.102 into minus 6 to the power half, it is square root. So, it is 49.5 ohm, right. So, surge impedance, first you have to compute surge impedance of the cable as well as surge impedance of the overhead line, right. Next is that velocity of the wave in the overhead line. You know that, say it is your this gamma 1, we know that 1 upon root over L1 C1, right. So, it is 1 upon L1 and C1, L1 was millihenry. So, 2 into the minus 3 into 0.01 into microfarad. So, into 10 to the minus 6 to the power half. So, it is coming 2.24 into 10 to the power 5 kilometer per second. Similarly, velocity of the wave in the cable 2, it is given as 1 upon root over L2 C2 is equal to 1 upon 0.25 into 10 to the power minus 3 into 0.102 into 10 to the power minus 6, because this is 0.25 millihenry. So, multiplied by 10 to the power minus 3, and this is microfarad. So, multiplied by 10 to the power minus 6 to the power half, it is coming 1.98 into 10 to the power 5 kilometer per second, right. After making all this, now waves originating in overhead line first, right. When the waves originate in the overhead line and travels towards the cable, we will have Z1 is equal to 447 ohm and Z2 is equal to 49.5 ohm, right. Now, it is given the incident voltage in the overhead line, it is given 100 kV. This data is given that it is maximum value of 100 kV travels, right. So, incident voltage of the overhead line, that is Vf is equal to 100 kilovolt. Now, therefore, incident current, right, in the overhead line If is equal to Vf upon Z1, this all relationship we know. So, it is 100 kV. So, make it volt, 100,000 by 447 ohm, that is 223.7 ampere. Now, transmitted value. Now, line to cable transmission factor, that is refraction coefficient for voltage, we know that tau V1, it is actually 2 Z2 upon Z1 plus Z2, this we have seen earlier. So, Z2 is for the impedance of the cable. So, 2 into 49.5 divided by 447, that is that Z1 surge impedance of the overhead line, and Z2 is the surge impedance of the cable. So, 49.5, that is actually tau V1 is coming 0.1994, right. Similarly, transmitted voltage in the cable, therefore, V is equal to, it will be tau V1 into Vf. So, this tau V1 is 0.1994 and Vf is equal to 100 kV. So, it is 19.4 kV, right. So, line to cable transmission factor for current, the tau I1 we are making it, it is line to cable transmission for current only, it will be tau I1 will be 2 Z1, that is your upon Z1 plus Z2, that is 2 into 447 divided by 447 plus 49.5, that comes 1.8006. Actually earlier we have seen that tau for your reflection factor, for the refraction coefficient for the voltage and for the current is it is 2, right. Basically tau V1 plus tau I1 is equal to 2. So, if you add these two 1.8006 and 0.1994, it will become 2. So, once you calculate this, there is no need to calculate this one, directly you can find out tau 1 is equal to 2 minus TV1, that will give you the same value, right. But for your understanding, I have just make it tau I1 is equal to 2 Z1 upon Z1 plus Z2, hence it is 1.8006. But earlier we have proved that tau V1 plus tau I1, it is actually 2. So, we find out one, another one to get that subtract from 2, right. So, that is 1.8006. Therefore, transmitted current in the cable I is equal to tau I1 into IF, that is tau I1 is 1.8006 into 223.7, right, because IF is equal to, we have computed 223.7 ampere. So, it is actually 402.8 ampere. So, alternatively what you can do is look for checking, other way you can do it, I is equal to V upon Z2, Z2 is the surge impedance of the cable and refracted voltage is actually we got 19.94 kV, just we have got it. So, make it in volt, divide by 49.5, you will get 402.8 ampere, same, this is alternate calculation, right. The way you want you can do it. So, alternately V upon Z2, but V is the here your refracted that your what you call this refracted voltage, this one the transmitted voltage, right, or refracted voltage, whatever you call, that is 19.4 kV. So, it means same thing you will get, this is and the same thing you will get, either this way you can compute or directly you can compute this way. Now, reflected values. Now, reflection factor for voltage, we know the formula for voltage, it will be Z2 minus Z1 upon Z1 plus Z2, this we have seen earlier. So, Z2 is equal to 49.5 and Z1 is equal to 447. So, 49.5 minus 447 divided by Z1 plus Z2. So, 447 plus 49.5, that comes actually minus 0.8006. Therefore, voltage reflected the overhead line, that Vb is equal to rho V1 into Vf. So, it is minus 0.8006 into 100 kV it is. So, minus 80.06 kV. Now, reflection factor for the current, it will be just your what you call negative of this one, negative, that means it will be 0.8006, we have seen earlier. If this is negative, then for current it will be positive. So, it will be Z1 minus Z2 upon Z1 plus Z2, actually it is minus rho V1, it is equal to 0.8006, right. So, once you get this, then that current reflected back in the overhead line, that I V will be equal to minus V B upon Z1 is equal to minus in bracket minus 80.06 upon 447. So, 179.1 ampere, right. So, now and the diagram voltage and current distribution, it initially the travelling wave 100 kV, but voltage 80.06 is reflecting back, right, this one that is your minus 80.06 kV. So, ultimately resultant here V will be your, this is that your what you call that this is the overhead line, this is cable and this is the junction, right. So, I made it like this. So, this is your 19.94 kV. Similarly, for the current, that 223.7, but reflected current was your this much, your here it is 179.1 ampere. So, it is actually 223.7 plus this height is your 402.8 ampere. So, this is your current wave and this is your voltage wave, right. So, this is actually I have marked as a figure 17. So, this is that current and voltage wave form, right. It is a step function we have considered, right. Once this transient over voltage is over, so next we will come to your what you call that insulation coordination, right. So, first thing is that basic impulse insulation level, in short we call BIL, BIL, right. So, reference your insulation level expressed in impulse crest, that is the peak voltage, right, with a standard wave not longer than 1.2 into 50 microsecond. This we have seen earlier, right, that is crest value or peak value reaches in 1.2 microsecond and 50% of that reaches in 50 microsecond, right. So, that is we call, that is 1.2 into 50 microsecond wave, right. So, that means insulation level expressed in impulse crest peak value with a standard wave not longer than this one, I mean 1.2 into 50 microsecond, right, wave. It is determined by test made using impulses of 1.2 into 50 microsecond waves. So, actually this is very, this is recommended, but in reality when you will try, it may not be exactly this 1.2 and into 50, but around that value it will be there, right. So, particularly for transformer impulse test, if you do so, you may not get that ideal value, but this is the standard, you have to see around that only. So, BIL, that is your basic impulse insulation level, usually defined as a per unit of maximum value of the line to neutral voltage, right. That is, for example, say for 340 kV line, suppose 340 kV, say it is 1 pu is equal to first this 345 by root 3. So, line to neutral you make, then multiplying by root 2, that means the peak value. So, it will be 282 kV, that is 1 pu per unit. For a example 340, if it is a 345 kV, then 345 by root 3 is the your line to neutral voltage, that is phase voltage, and multiply by root 2. So, it will be its peak value, that is 282 kV. So, that suppose if you have BIL of 2.7 pu, that means 2.7 into 282, that will give you, because 1 pu is equal to 282 kV. So, that will give you 760 kV, right. So, this is your idea of basic your impulse insulation level. Now, next one is withstand voltage, right. Therefore, the BIL that can be repeatedly applied to an equipment without any flashover, then disruptive charge, puncture or other electrical failure under specified test condition, right. So, whenever they are testing the equipment, they test all sort of things. So, this is actually withstand voltage. Now, another thing is chopped wave insulation level, right. In this case, it is what happen, it is determined by the test using waves of the same shape means that 1.2 into your that 50 microsecond, that the wave shape, right, to determine the BIL, right. So, that is basic impulse insulation level, right. So, with the exception that the wave is chopped after 3 microsecond, that means it is applied, but after that it is chopped at 3 microsecond. So, if there is no information, the chopped wave level is assumed to be 1.15 times the BIL for say oil field equipment, for example, transformer. So, it is assumed to be equal to the BIL for the dry type insulation. So, some experimental setup they do and they take 1.15 times for the chopped wave, right. If there is no information you get, they will assume that it is 1.15 times the BIL for oil field equipment, for example, transformer, right. So, now then critical flashover voltage, they call CFO, right. The peak voltage for a 50% probability of flashover or disruptive discharge, this is called your critical flashover voltage. Now, impulse ratio for flashover or puncture of insulation, impulse ratio, it is the ratio of impulse peak voltage to the peak value. Listen, it is the ratio of the impulse peak voltage whatever you have to the peak value of the 50 to 6, either 50 hertz system or 60 hertz system. That is why I am making it 50/60 hertz voltage to cause flashover or puncture, right. So, in other words, it is the ratio of breakdown voltage at surge frequency to breakdown voltage at normal system frequency, because when you are considering that is the ratio of impulse peak voltage, right. So, basically it is the breakdown voltage at the surge frequency to the breakdown voltage at normal system frequency. This is that called impulse ratio. So, this is theory only, not numericals, but you have to know all these things, right. Now, insulation, next is insulation coordination. This is quite important. So, insulation coordination is the process of determining the proper insulation level of various components in a power system and their arrangement. So, in other words, it is the selection of an insulation structure that will withstand the voltage stresses, right, to which the system or equipment will be subjected together with the proper surge arrestor. Actually, in this course lightning arrestor will not cover, right, but you have the, if you go to any power station or substation, you will find lightning arrestor is there, right. So, that is why, in other words, it is the selection of an insulation structure that will withstand the voltage stresses to which the system or equipment will be subjected together with the proper surge arrestor. That means, particularly this maximum switch or impulse or surge comes due to the lightning stroke. So, that is why the lightning arrestor is designed in such a fashion such that it can protect the equipment, and they when they design all sort of things, they consider all the worst cases. Accordingly, that surge arrestor rating will be determined such that it can protect the equipment in the say substation, for example, say, right. This process is determined from the known characteristic of voltage sources and the characteristic of surge arresters, right. So, different type of your what you call lightning arresters are there, but that is beyond the scope of this course. Now, there are three different voltage stresses to consider when determining the insulation and electrical clearances requirement. First thing is for the design of high voltage transmission line. One is the 50 or 60 hertz power voltage, lightning surge voltage and switching surge voltage. Different type of switching is there in the literature also, but I have skipped those things, then it will consume more time for this, but whatever basic things are there, whatever actually we need to learn, those things only we will see that. So, lightning surge voltage and switching surge voltage, but this lightning surge voltage is a very severe one. Therefore, insulation for transmission system must be chosen after a careful study of both the transient and power frequency voltage stresses on each insulation element. So, one has to, but insulation is a I mean it is a we power comes, but there are many technical things are there, and this insulation is one of the main thing, right, to particularly the protect from the fault from this kind of lightning stroke or switching surges, right. So, those kind of thing insulation plays a significant role. So, in general lightning impulse voltage have the highest values and the highest rate of voltage rise. So, lightning stroke is the severe one among all of this, right. So, therefore, a properly done insulation coordination provides the following: the assurance that the insulation provided will withstand all normal operating stresses and the majority of abnormal ones. That means, whatever insulation you make, that it will withstand the normal operating stresses, right, as well as majority of abnormal ones. I told you that it may be switching surges, lightning surges or some fault, right. So, all abnormal it will sustain. Then the efficient discharge of over voltages due to the lightning and switching surges as well as other your what you call internal causes. So, that also efficient discharge of over voltages due to the lightning and switching surges as well as other internal causes. So, all these things insulation has to sustain, right, it has to withstand all sort of things. Number 3 is the breakdown will occur only due to the external flashover. There is a possibility of breakdown due to the external flashover, right. And second thing is that the positions at which breakdown take place will be where breakdown may cause no or comparatively minor damage. If there is a breakdown also, the damage should be minor, right, but occasionally it happens your what you call, for example, when I was listening some lecture from renowned person, say when it is a very interesting thing. Suppose when you are testing, suppose you have tested say 200 same equipment, say up to 200 numbers, right. As soon as when you are testing, you find that your testing is okay, but after suppose 200 the same equipment, right, and but after the testing you do not know out of the 200 that 1 or 2 might have got damage, but you do not know because when you are testing it was okay. So, these are called hidden kind of fault in that equipment. So, there is a possibility of that thing also, right. So, but anyway when we test at the time we found everything is clear, but we do not know, maybe out of several same equipment, maybe one or two have become defective after the test. That is not, because we are not testing after that, directly we are going for your installing that, right. So, these are called hidden fault, but we will not discuss about those things. So, thus the insulation coordination actually involves the following. First thing is the determination of line insulation, selection of the bill value and insulation levels of other apparatus, and selection of lightning arresters. This lightning arrestor will not study in this course, but the selection of we have to design that proper rating of the lightning arrestor. So, for transmission line say up to 345 kV, the line insulation is determined by lightning flashover rate only, but if it is above at 345 kV, the line insulation may be dictated by either switching surge consideration or by the lightning flashover rate, right. So, because voltage level is very high, so insulation level whatever you see, it will be dictated by switching surge consideration or by the lightning flashover rate, right. So, that actually they are testing at that how long that insulation can sustain at that your what you call at that voltage level. I do not know whether you have seen that insulation of transformer winding or not, how they make the insulation for the transformer winding. If you have anything, you can see one open transformer winding, and each winding how they are insulated, right. Then you will have some good ideas about insulation thing. Insulation plays a very significant role. So, above 345 kV, switching surges become the major factor of flashover consideration and will more likely control the insulation design. So, if voltage level is above 345 kV say, then of course, switching surges become the major factor in flashover consideration, right. So, now the probability of flashover due to a switching surge is a function of the line insulation characteristic and the magnitude of the surges expected, right. So, the number of insulators employed may be selected to keep the probability of flashover from switching surges very low. So, all these factors actually you have to consider. Now, switching surge impulse insulation strength is based on tests that have been made on simulated towers. So, all sort of tests you have to make it, right. Switching surge impulse insulation strength is based on tests that have been made on simulated towers. So, all sort of before you put it in installation, that you have to consider that all sort of factors, all sort of testing. Just directly manufacturing and you are not putting it, after that you have to test it whether it can sustain or not, all those high voltage stresses. Now, an extra high voltage levels and increase in insulation length, right, does not provide a proportional increase in switching surge withstand strength. That means, just like increasing the insulation length does not mean that proportionally it will increase the switching surge strength. This is due to the electric field distortion caused by the proximity of the tower surfaces and is called the proximity effect. Since the proximity effect is not related to the lightning impulses, so switching surge considerations dictate the insulation values at the extra high voltage levels. So, at the extra high voltage level, switching surge thing is the main concern for the insulation. The maximum switching surge level used in the design of a substation is either the maximum surge that can take place on the system or the protective level of the arrestor, that is lightning arrestor, which is the maximum switching surge the arrestor will allow into the station. So, you have to design that lightning arrestor in such a fashion that it can maximum switching surge that the arrestor can allow. Some current rating you have to choose, different type of arrestors are there. So, these are the significant thing, but I have seen in substation that lightning arrestor also, due to that heavy lightning stroke, I have seen that even arrestor also, lightning arrestor also failed. This I have seen in the past, right. Somewhere in the substation we found due to that arrestor failure, some other equipment also got damaged. So, one has to be very careful for designing all sort of thing, particularly to protect all the equipments, that is due to your lightning stroke, switching surges, etc. right. Therefore, the coordination of insulation in a substation means the selection of the minimum arrestor rating applicable to withstand 50 or 60 hertz voltage, and the choice of equipment have an insulation level that can be protected by the arrestor. So, arrestor design, lightning arrestor selection is main important in substation, right. So, transient network analyzer can also be used to study the switching surge level that can take place at the substation, right. The result may be used to determine and coordinate proper impulse insulation and switching surge strength required in substation apparatus. If you go to any substation, you will find these lightning arresters are there, right, and you will see, once you visit, just apparently from the distance you do not know, you go and see all these things like lightning arresters, then CT, that is current transformer, then potential transformer, how the current transformers are connected, then the insulators, then the transformer, circuit breakers, each and everything, and one can learn, right. So, distance between the arrestor location and the protected insulation affects the voltage imposed on insulation due to reflections. Look, so many things are there, right. So, the severity of the surge depends on how well the substation is shielded, right. That means, you have to protect the substation, insulation level of the substation structure and the incoming line insulation. So, all these things one has to consider. One is that insulation level of the substation structure and the incoming line insulation. For a travelling wave coming into a dead end station, that is coming at the substation end, right. So, dead end station, the discharge current into arrestor is determined by the maximum voltage that the line insulation can allow, right. So, whatever is the maximum voltage or stress that line insulation can allow, based on that only arrestor, your what you call a lightning arrestor current is determined, right, by the surge impedance of the line and by the voltage characteristic of the arrestor, right. So, therefore, the discharge current of an arrestor, just I am writing, can be expressed as, it is generally given as V is equal to I arrestor, lightning arrestor is equal to 2 V minus VAR upon JC. That is, V actually is equal to magnitude of your incoming surge voltage and VAR is arrestor terminal voltage. So, this way, therefore, this your IAR is the arrestor current, V is the magnitude of incoming surge voltage, VR is arrestor terminal voltage and ZC is the surge impedance of the line. So, figure 17 shows the insulation coordination, figure 17 I will show you, shows the insulation coordination between an oil field equipment, for example, transformer and a surge arrestor, right. The arrestor impulse spark over voltage is compared to the chopped wave test level of the transformer. A more meaningful comparison is to compare the arrestor spark over with the wavefront test. That means, this is that this is actually this is figure, it is figure 18 actually, it should be figure 18, this is figure 18, right. So, in this case, if you look into this, that your wavefront, this is that wavefront withstand voltage, right. So, next is maybe it is reaching to your what you call at some withstand voltage time curve of equipment, then this one is the chopped wave withstand and this is the bill, the full wave withstand, and this curve is discharge voltage characteristic of the arrestor, right. This is wavefront spark over this voltage, this side is voltage in per unit, this side is the time in your microsecond, this is the impulse voltage wave rising, it is rising, and this is your maximum voltage discharge, this point, because if you look in the curve, this is the maximum voltage discharge and this is the discharge voltage characteristic of the your arrestor. So, this is the minimum margin of the protection scheme, this gap is the minimum, this is the withstand voltage time curve of equipment, this is a chopped wave withstand, right. At this point, suppose wave is chopped. So, this is a chopped wave withstand and this is a wavefront withstand. So, this is actually figure 18, this is illustration of insulation coordination between oil field equipment and surge arrestor, this is based for the transformer, right. So, all these things one has to understand here, not much mathematics here, only little bit theory and understanding. So, thank you very much, we will be back again.